You're welcome, everyone. Thanks for attending our today's session. So in this session, you're going to learn about how we create our RNN models on location predictive analytics using NVIDIA's GPUs. So it will require you to have some kind of knowledge about machine learning and RNN models training. We've got a great speaker today, Dirk Technica, who is going to speak today about RNN training on location prediction technology. Dirk is a very experienced technical engineer who is skilled in object-oriented programming, service integrations, and agile development lifecycle. He is currently working for Pointr as a technical lead. So very quickly, my name is Eva, and I am the marketing manager of Pointr. At Pointr, what we do is we build software that do interlocation. We are not an app developer. We are not a hardware manufacturer. We just do software for location technology. We've been doing it for 8 years. So we're deployed in around 1,000 different buildings around the world with over 2 million of daily users of our technology. And of course, we're seeing a huge boom in location services and analytics in smart workplaces, healthcare, retail, and aviation right now. So our headquarters is in London. I'm based in London. We have our CEO in Boston, our tech team in Istanbul, and we have support from all over the world along with our partners. So in terms of where we are present, at Pointr, we deliver location technology for many different blue chip clients globally with different sectors and the geographies. So we have UC Health in Colorado for healthcare, CBRE in their office space sector, and then retail, aviations, they all represented when it comes to interlocation. So what do we do? Firstly, we create maps based on floor plans. We do that in an automatic and a very quick way. So if you want to know where your things at in your building, we just need the CAD files, and we can do that for you fairly quickly. If you have a map, and then we can add a blue dot on top of it. So that would be your instant locations, so you can see where you are. When you have your interlocation and the maps, and you can then do the wayfinding, this will help you to get from A to B, or help you understand where your things are and how to navigate there. So we can do this both indoors and outdoors. We also do asset tracking, which will help you to track equipment and people in your venue using either a Bluetooth tag or Bluetooth device. So for geofence, which is very important for your location-based notifications and location analytics. For example, you can create a geofence to cover a lobby or a car park. When a visitor moves into the geofence, and then the geofence would trigger a notification, welcome to the airport, click this button to navigate to your check-in counter, etc. So this would also be used in location analytics, which Dirk will be able to talk more about it in details for the following presentations. And finally, for the location analytics, it would help you to know how people use or interact within your venue and with your facilities, and how they move around in your space. So for example, you can know how crowded your space is right now, and how long is the queue in front of the security lines. So operational manager could decide whether he or she would send support to this area and something like that. And now I'm going to hand it over to Dirk, who will be able to introduce how we train our RNN models for our location predictive analytics technology, and why we're using NVIDIA's GPUs for this process.
Hello everyone, my name is Dork and I work as a technical team lead at Pointr, and today I'm going to talk about how we use NVIDIA's graphic processing units to accelerate our calculation and how do we use in our applications. So at Pointr, we have several products which work seamlessly and interacts with each other. One of these products is our deep analytics engine, and it uses NVIDIA technologies. So to begin with, our deep location platform covers all these products, and we are able to predict device locations, basically 1 to 3 meters for Bluetooth and 5 to 8 meters for Wi-Fi analytics. The devices I'm talking about basically covers all the electronic products which emits either Bluetooth or Wi-Fi signals, such as mobile phones, tablets, laptops, headphones, beacons, and stuff, other electronic stuff like that. Inside our deep location platform, one of our products is our deep analytics engine, and we use NVIDIA's GPUs to enable more efficient RNN training. And I will talk about some modules inside our deep location engine. We basically use NVIDIA's GPUs to do two simple, not so simple things. One of them is to accelerate our recurrent neural network trainings, and the other one is basically calculates lots chunks of data for our some use cases, which I will talk about. Our deep location engine consists of 4 microservices, which are first 3. Basically, the first 3 I'm going to talk about is our smart segmentation service, our prediction service, and our correction service. And our recommendation service is currently under development, so we will possibly use NVIDIA's CUDA framework as well here. So these 4 services are written in Python and uses MongoDB as databases. And we have some libraries used by these services. So these services integrate with our main product, Pointr Cloud, through web services, JSON-based web services. And I'm going to talk about our deep analytics smart segmentation service, which is DASS first. So deep analytics smart segmentation basically uses our location data and produces different kinds of reports. Flask API is used for integration with our Pointr Cloud and also other deep analytics web microservices. For graphical user interface, we use Flower, and for report queuing, we use Celery. Also, as other microservices under deep analytics, we use Mongo as our database. So deep analytics smart segmentation calculates 5 different kinds of reports. And during the calculation of these reports, we use NVIDIA's CUDA framework and utilize our GPU because our location data is huge. Basically, we gather almost over 500 million positional data through a year. So I'm going to talk about our first report for deep analytics smart segmentation, which is footfall-based clustering report. So for footfall-based clustering report, we use k-means algorithm and also utilize NVIDIA's GPU to calculate faster because, as I said before, we have quite a bit of data. And for footfall-based clustering report, we try to calculate. By the way, these samples are from a major airport, so you will see airport-related information in the samples. So for footfall-based clustering report, we basically a passenger in the airport is considered to be as in a specific zone if he or she visits there for at least 15 minutes. And in this report, we calculate how many of the passengers being in a certain zone, like economy passenger or check-in zone or gate zone. So For reading this report, for example, if we talk about the first row, approximately 50,000 people were present at both economy passenger and check-in tagged zones inside the airport, and these constitutes all of the people that were present in economy passenger tagged zones, and 56% of the people that were present in the check-in tagged zones. So what we do is basically we read signals from passengers' mobile devices, mostly in the airport, and we do not know passenger information such as gender, age, or name, and such crucial information. But what we know is the MAC address of the device of the passenger. For example, the Wi-Fi MAC address for the mobile phone of the passenger. So we have some zones in the airport, and we tag them with keywords such as check-in, gate, or for example, if you are sitting in a Starbucks, we give a tag like food and beverage or coffee. So through these zones and through these keywords, we know how many of the passengers visit which kind of zones. For example, if we talk about a mall, which we, as Pointr, we operate also in malls and hospitals, we can also differentiate with other stuff like, for example, in malls, we can say parking, or for example, if you visit a high price department such as Gucci or Louis Vuitton, we can tag it as high price customer. Or for example, if you visit a theater, we can tag it like entertainment. So basically, we are trying to figure out how many passengers or customers visit which kinds of zones. So this is basically based on footfall, which is if you visit some place for 15 minutes, which means you do not pass by that zone, you spend some time. So we consider that device as a footfall record for that specific zone. So this is the first report for Deep Analytics Smart Segmentation Service. And as I said before, we use k-means clustering algorithm to basically cluster data in a smart way. So the second report is our percentage report. Percentage reports works in three different ways, which is forward, backwards, and bidirectional. And what we do is, as you can see from the right side of the screen, we have a report which runs in forward only option, and we have some percentages. To read this report, we can, for example, if you see the JSON data, the passengers visited check-in zones are approximately 35% of total passengers, and of these 35% passengers, 83% of them visited a zone tagged security after visiting the check-in zone. I'm saying after because this report is in forward mode. If I say, let's say, in backward mode, then I will say that some percent of passengers, economy passenger visits happened before check-in visits. So I'm evaluating this report as in forward mode. So we said that 36% of total passengers visited check-in zone, and then 84% of these passengers visited an economy passenger tagged zone right after visiting a check-in zone. And of these 84% of passengers, approximately 15% of them visited a zone which is tagged security, for like we tag security for passport control and stuff like that in airports. So basically, this shows passengers' common flows inside the venue, and this is also operational in malls and hospitals and other venues as well. So this report is similar to percentage report, but gives us the most common paths of passengers inside the airport. So basically, we state a starting point, which is check-in, and end point, which is gate for this example. So we are trying to figure out the common 5 paths, starting with a zone tagged check-in and ending in a zone tagged with gate. Basically, this is for the departure flow inside the airport. For let's say an arrival, we will start with gate and end with just exit of the airport, or cab zone in the airport. So what we see in this example is about 32% of the passengers follow the path, check-in, security, and gate inside the airport that day. All these reports, I'm talking about inside Deep Analytics Smart Segmentation, runs daily, but we have the option to run them monthly and yearly. So this gives us the information of the most common paths followed by passengers inside the airport. There's an option to not give a start and end keywords inside sequence report. In that case, we produce most common paths, but the starting node and the ending node of the sequence are not strict. So if we let's say, calculate a complete path, this report focuses on exclusive start and end zones, while in partial path, it does not pick exclusive start and end zones. So there is this option for sequence report. Well, this report is a little bit interesting, and I think some of them will find it very useful. So what we do here is we have some keywords, as you can see in the metrics, such as baggage, pharmacy, business passenger, and other keywords. So we try to find related keywords according to the data we have. So if we have a number close to +1, this means there's a direct correlation between these two keywords, which means a passenger or customer visited some of these keywords, also visited the related keyword as well. So if there's a -1, which means there's a negative correlation between these two words, which is if one passenger visits some keyword, then we expect that passenger or customer do not visit related keyword. If there's a value approximately 0, this means that there is no correlation between these two keywords. So as you can see in the metrics, there's a high correlation between business passenger and gold check-in, which makes sense. So the other keywords, as you can see, is close to 0, but in this sample, we only gave 8 keywords, but we have hundreds of keywords for our zones. So producing this matrix takes a lot of time if we do not use our GPU, NVIDIA GPU. So for all these reports, since the data we work with is huge, we harness the graphical processing units power. So another report in Deep Analytics Smart Segmentation is conversion rate report, which gives us information about a keyword such as as you can see in the bottom of the screen in the Excel files, which is basically the A1 gate in the airport. So conversion report works in three directions as well, like forwards, backwards, and bidirectional. So what we see here is, if you see the first row, which is gate, we see that passengers visited A1 zone, visited a tag, gate-related tag right after visiting A1, which is a conversion rate of 65%, and that corresponds to almost 850 passengers. Let's say you apply this to a mall, then I can say that if lots of customers visits, let's say, a coffee place after eating some stuff in the mall, then I have the option for our clients, basically the mall itself, to promote a coffee place if we detect that customer in the food and beverage section, or let's say if I detect customer in parking space, then I assume that this customer is either a medium price tag customer or a high price tag customer. So I may expect him or her to visit medium price or high price tag departments. So this is another report, and this report is currently live in one of the largest airports in the Middle East region. This airport has over 70,000 passengers daily, and basically we did a custom type of report. And this use case basically shows that for a passenger, as you can see, we only know this passenger's MAC address, as you can see in the fourth row, and we do not know the passenger details. So this passenger is sniffed, the passenger's device is sniffed throughout the airport from start to the end, and we can match these passengers in the gate with flights. Basically, we reconcile flights with passengers, and as you can see, for example, in Emirates flight 384, this passenger entered the airport at in first entry time value, and we collect this passengers information in check-in areas, security areas, gate areas, and also we are able to give information like, for example, how much of the, let's say, Germany passengers spend in security, in check-in, how much time they spend in duty free, and so on. So basically, this generates more revenue for airport, which is Pointr's client, so that they can arrange their flights and their gates and make passengers spend more time in areas which they spend more money, like duty free and stuff. So the second service I'm going to talk about is Deep Analytics Correction Service, which you can see the overall architecture. As you can see in the graphic, we sniff Bluetooth beacons and Wi-Fi devices to our own POP devices, which are sniffers capable of sniffing Bluetooth and Wi-Fi data. Also, it's possible to use other partner access points. We currently work with several of them. So if your venue has some other firms' access points, we can work with them as well. So this partner access point sends the sniff data through our virtual POP integration to our main Pointr cloud product, and we generate positions from these sniffed Bluetooth and Wi-Fi signals, and we feed them to our position cache. Also, this position cache interacts with our deep analytics correction service. So basically what deep analytics correction service does is to complete blank positional data spots by using recurrent neural network models trained earlier. So we train these RNN models daily, and we use this daily trained RNN models throughout the day to complete missing data. So some devices cannot be sniffed due to physical environment, and we are able to find out where these devices were at that time, so we can produce more accurate analytics results. So this deep analytics correction service uses positional data. Positional data you can think as an XY coordinates and a timestamp and a MAC address is a positional data. And these positions are sent to Pointr cloud, and deep analytics correction service also feeds them to Mongo database, and we train our RNN models daily. And during the day, the day before RNN model is used to complete basically the missing positional data throughout the day. So when we produce these reports, our reports become much more accurate, and we can provide much more analytical results. So basically, data flow in correction service is we receive positional data from Pointr cloud, and this then restore these positional data in Mongo database, and we train RNN data daily and send the completed data to Pointr cloud afterwards. So for RNN training for correction service, of course, NVIDIA's GPUs has a high speed advantage over the traditional CPU processes. It's almost tenfold at the moment. So basically, it's not possible to train these RNNs daily if we use CPUs. So currently, it takes almost an hour to train our neural networks daily, and we do this at midnight. For RNN generation for deep analytics correction service, we cluster these RNNs for by three different types of properties. One of them is the facility internal identifiers. Facilities are basically different buildings of the same venue. Let's say if you are an airport and you have three terminals, like terminal 1, 2, and 3, each of these terminals will be a separate facility. The second property of RNN clusters is levels. Levels is basically floor numbers of that building. And the third property is position type. Another product of Pointr is our mobile product, which we call SDK. And also we have Wi-Fi and BLE position types. Also, we are able to track assets with Pointr Cloud. If you have wheelchairs or in an airport or other stuff, let's say, to track specific objects inside your venue, we can track them, and it's possible to track both Wi-Fi objects and BLE beacons. So we have asset Wi-Fi type and asset BLE type as well. So for RNN training, what we do is we import data points from Pointr Cloud and RNN models from our Redis cache. We use Redis because it's a persistent cache mechanism. And first of all, we shuffle and partition this data based on these three cluster properties, which are facilities, levels, and position types. Then our GPUs train these processes concurrently at the same time. Of course, since we use NVIDIA's GPUs, it makes much more sense to use NVIDIA's CUDA framework versus, let's say, another framework such as OpenGL or something like that, because CUDA framework allows us to really get the best of our NVIDIA GPUs. So after GPUs training process complete, we have our RNN models ready, and we are able to predict the missing positions. And when we predict these missing data, missing positions, we send the completed positional data to Pointr Cloud to be used in other reports and other analytical results. And as I said before, we train on our RNN models daily, and these models are currently saved in our Mongo database. And each day we use the previous day RNN model to train our current RNN model as well. And it's like working, maybe some of you may know the LSTM model, long short-term memory model. So basically we use previous day data, which makes our RNN models more accurate each day. And we, after training the RNN model, we of course update our Redis cache so that the next day's data will be completed more accurately. So during RNN training, what we do is we gather some positional data. As you can see, the timestamps here are stated as T1, T2, T3, and so on. So we use concurrent positional data to train our RNNs, and we do not use the sequence of position data if they have a missing data point in between. So basically the most correct data is used to train our neural network models. And we are trying to, after training our RNNs, our goal is basically to fill out the missing data points in all sequences. So if, let's say, there's a missing point between after the third timestamp, then we input these three positional data to the RNN model, which we trained earlier, and figure out the missing data point. So if we do not have some concurrent data, we have some, let's say, missing data points between timestamps, then it's not fed into the network model. So as you can see in the right side of the screen, we need to have some concurrent data points to be suitable for our recurrent neural network model. So the third service I'm going to talk about is our deep analytics prediction service. Okay, so the third microservice I'm going to talk about is our deep analytics prediction service, which is basically doing two things. One of them is predicting certain passengers or customers' next zone, and this runs individually for each customer, each device. And also we are able to predict group-based behaviors. For example, if you want to know how many customers will I have in half an hour in a Saturday in our mall, then this is group-based behavior. In user-based behavior, we are trying to predict if, let's say, one customer visited a zone tagged food and beverage and then spent 30 minutes and then visited another zone tagged, let's say, coffee, and spent 10 minutes there. So we are trying to predict where will this customer be in, let's say, 15 minutes. So this works in a similar way with our correction service. the recurrent neural network model trains daily here as well. But this prediction service uses not positional data, but another data which we call analytics zone data. And this data is produced by Pointr Cloud and fed through its API to the prediction service. And this data basically gives us information about how many minutes certain customers spent in which zone. And so we retrieve this analytical zone data periodically in every 5 minutes from Pointr Cloud API to the prediction service. And we do an incident analysis in every 15 minutes. And then we try to predict our user-based and group-based behaviors, which is also 15 minutes in frequency. And the RNN model here is also runs nightly, which is daily. And so during the training of RNN model here, we also use NVIDIA's GPUs to basically do it faster. So there are two patterns. One of them is footfall pattern. As I said before, this basically relies on a certain device's zone visit probability predictions. And in this pattern, visit order is highly important. So if one passenger or customer visited zone A, then B, then C, it will differ in our RNN model. So this is for use-based prediction, and also it's applicable to group-based predictions as well. Then through using our RNN model, if that group of devices or a single device visited zone C at last, then we try to predict which zone he or she will be right after zone C. For example, in this example, we see that there's a 30% probability that zone E will be visited, and there's 60% probability that zone F will be visited. The other pattern is dwell time pattern, which basically relies on the time a device has spent in a certain zone. So different intervals will yield into different results for the RNN. So let's say if one customer spends 12 minutes in zone A, then 8 minutes in zone B, and then 6 minutes in zone Z, the probabilities will be different than spending different times in zone A, B, and C. And so we have to basically train different RNN models for different cases here. So if we do not use NVIDIA's GPUs and CUDA framework here, it's not possible to concurrently train these RNN models at the same time. Yeah, I will switch back to Eva at that point, and she will give information about some use cases using our microservices, deep analytics microservices.
All right. Thank you very much, Dirk, for this very thorough presentation about how we train our RNN models using NVIDIA's GPUs to improve our location prediction technology. So in terms of location predictions use cases, I believe Dirk has already mentioned a bit about that when he was presenting the use cases of our project in one of the biggest airports in the Middle East region. So here I'm just gonna be very quickly to wrap up how we can utilize location prediction technology to enable different kinds of location analytics features, such as you can visualize where your visitors or your employees tend to go in the venue using the heat map. and you can have the footfall analytics or path analytics to understand which routes is the most popular path or for your visitors or your employees. And in that case, you can predict when or where would be the most likely area to get like long queue or overcrowded situation, so that you can decide whether you want to assign more supports in that area during a certain period of time, etc. So finally, it's wonderful that we're invited to this event, and I want to take the chance to thank NVIDIA's team for their brilliant support and providing this amazing platform and opportunity. So we are very excited about this, and we are very excited to be here today. Also, we'd like to thank all the attendees who joined this session with us today. If you feel like learning about more details, please feel free to get in touch with us. Apart from that, thank you very much, and hope you guys have a lovely day. Bye-bye.